Okay, so let us carry on our discussion on differential amplifier. So far we have discussed BJT based differential amplifiers. Now let us also talk about MOSFET based differential amplifiers. Okay. And the analysis will be similar to what we had done for BJT based differential pairs. So let us try to find out the common mode response of a MOS differential pair where we have transistor M1, a MOSFET, N-type. Okay. Similarly, M2 also N-type MOSFET. We have drain resistances RD, okay, and the common mode input that is applied on the gates of both these transistors. So same input is applied, and we had studied earlier that if the input is same or in a common mode where there is no difference between the magnitude or phase of the input which is applied on M1 and M2, then the output is 0. Okay, I mean the differential output is 0. Okay, because the output on X and Y, so both are equal, and the differential output will give the output as 0. Okay. And let us say that a tail current is also attached here, ISS. So one can find out the potential at this point X and Y by knowing that current through each transistor is ISS by 2, that is half of the tail current. So one can find out this potential, which will be equal to VDD minus drop across this drain resistance. So one can write Vx as VDD minus ISS by 2 times RD. Okay. And Vy also would be same, that is VDD minus IS by 2 times RD. And the differential output V out. Okay, so the differential output V out would be equal to Vx minus Vy, which is 0. Okay. So similar to what we had seen in BJT based differential stage. Now one can also find out the equilibrium overdrive voltage. Okay. So we understand that in a MOSFET, overdrive voltage is given by this relation VGS minus VT. So this is called overdrive voltage. Okay. Now we want to find out the equilibrium overdrive voltage. Okay. So this equilibrium overdrive voltage here means that the voltages that are seen at the inputs of these two transistors, so that both of these transistors carry a current equal to ISS by 2. Okay. That is, this equilibrium overdrive voltage is the voltage seen by M1 and M2 at the input, okay, which causes this tail current to flow equally in these two transistors. That is, half of the current flows through M1 and half of the current flows through M2. Okay. Now for finding out this equilibrium overdrive voltage, we need to also ensure that both the MOSFETs are saturated. Okay. So for example, let us say M1 is saturated. Okay. So I can write the drain current in saturation as mu n C aux, okay, W by L VGS minus VT whole square. Okay. So I can write this equation in saturation where ID saturation, so this is actually equal to this current, which is ISS by 2. So from this relation I can write VGS minus VT. Okay. So this 2 goes off from here. So VGS minus VT whole square is ISS by mu n. I'll write here VGS minus VT whole square is ISS by mu n C of WL. Okay. or if I remove this 2, then I'll have to take the square root of this, and if I bring this Vt also on the right hand side, so this Vth or Vt comes over here. So Vgs is now finally equal to this, or Vgs minus Vt in fact, so which is equal to this term only. Okay. So Vgs minus Vt is equilibrium overdrive voltage for which the current through these two transistors are ISS by 2. Okay. Okay. Now one can also find out the minimum common mode output voltage. Okay. That is minimum common mode output voltage, that is the output voltages which are appearing here. Okay, so this can be found, in fact minimum common mode output voltage, because this is actually the drain of these two transistors, and to keep this M1 or M2 in saturation, I need to ensure that drain to source bias, so that should be greater than or equal to VGS minus VT. So I can ensure that the MOSFET is in saturation if I ensure that VDS is greater than or equal to VGS minus VT. Okay. And this VDS, that is this drain voltage here, so that can be found by assuming that ISS by 2 flows through each transistor. So I can write this Vx as VDD minus IDRD, or VD of this is VDD minus IDRD. Okay, so I can replace this VD by VDS by VDD minus ISS by 2 times RD. ISS by 2 times RD. So this should be greater than or equal to the VGS minus VT. Okay. That is this common mode voltage VCM minus VT. Okay. Because S is common here for for both these two transistors. S is common. Okay. Source is common. Okay. So I can find out the another condition here, that is minimum common mode output voltage, that is this voltage. So this should be greater than the VCM minus VT, that is minimum, not minimum, common mode input voltage minus threshold voltage. Okay. So this will ensure that this MOSFET is always in saturation. Now we have also studied that this value, that is Vx or Vy, so this also limits the gain of this amplifier. So this value, that is minimum common mode output voltage, this will also limit the gain of this differential stage as well. Now similar to the BJT based differential pair, one can also draw the IV characteristics of a MOSFET based differential pair. Okay. So here in the MOSFET based differential pair also we have to understand that if this V in 1 is increasing, so that would mean that this, let us say this is ID1 and let us say this is ID2. Okay. So if V in 1 is increasing, so that would also mean ID1 should increase. So which would mean that this Vx will go down. Okay. Similarly, when V in 2, so this increases, so I can say that ID2 increases. Okay. Or this node potential Vy, this goes down. Okay. Now this also means when V in 1 is increasing, okay, so this would also mean that considering both these conditions, so this will also mean that in the first case ID2 will come down and Vy will increase. Okay. Similarly here ID1 should come down and Vx should increase. Okay. considering both these. So these things can also be plotted in terms of considering, let us say, current on the y-axis, okay, current on the y-axis, and the voltage, differential input voltage, V in 1 minus V in 2 on the x-axis. Okay. So one can plot IV characteristics. Okay. So this is the point where both V in 1 and V in 2 are equal, or V in minus V in 2 is 0, and this is also the point where, because of these two inputs are same, so the current drawn will also be same by the transistor, so which is ISS by 2. Okay. Now beyond this point, if I go to the right where V in 1 in is increasing, okay, so when V in 1 is increasing, so ID1 should increase. So this is ID1, so this is increasing, it increases up to ISS. Okay. Now at the same time, ID2 should decrease, so ID2 is decreasing, okay, because overall ID1 plus ID2 can only be equal to ISS, right? ID1 plus ID2 is ISS. So if ID1 is increasing, so ID2 has to decrease, so it decreases. Similarly, if I go towards the left to this point 0, that is V in 1 is V in 2, okay, so this means here V in 2 is increasing. So when V in 2 is increasing, so ID2 should increase, okay, so ID2 is increasing beyond this point and it reaches ISS. Okay. Now at the same time, ID1 should decrease, it is decreasing, right? Now one can also plot the differential input voltage versus the output at X and Y, these 2 points. Okay. So again, this is the point where V in 1 is equal to V in 2. Okay. That is why V in 1 minus V in 2 is 0. And at this point, equal currents flow through these two transistors. Okay. So that would mean that both Vx and Vy would be equal, and that would be equal to VDD minus ISS by 2 times RD. Okay. So VDD minus ISS by 2 times RD, that is this point. Okay. Both Vx and Vy are equal. Now beyond this point, if I move towards right, that is when V in 1 is increasing, I'll check here, V in 1 is increasing, so Vx should decrease and Vy should increase. Okay. So Vy, that is this is increasing, reaches up to VDD, and Vx, so this decreases, okay, decreases to this value, VDD minus ISS times RD. Okay. So this is also the point where Vx is 0, right? So Vx is 0, so that means so Vx is 0 here, okay, or V in is increasing here. So V in increases to a point that the current increases to ISS. So the current flowing through this is at this point ISS. So entire VDD drops across this, and not entire VDD. So Vx could be calculated as VDD minus I times RD, and I is ISS, okay, at this point. Okay. Now similarly, if I move from this point towards left, where V in, this was V in 1, V in 2 is increasing. So when V in 2 is increasing, I found that Vy should reduce and Vx should increase. So Vy is reducing, okay, and Vx is increasing, it reaches up to VDD. Okay. Fine. Now similar to a BJT differential pair where we had calculated the small signal response, so here also one can calculate the small signal response by considering a small signal input change, that is VCM, that is this input is rising by delta V amount and this input is falling by the same amount delta V. Okay. So this will change the drain current, that is here the drain current will increase by delta IC, and here the drain current will decrease by the same amount, that is delta IC. Okay. So one can then, in the small signal model, one can assume that if this is happening, that is because of signals rising and falling by the same amount on these two transistors, the current are rising and falling by the same amount. So this would mean that delta Vp, that is this Vp has to be AC ground. That is, there should be no change in the potential at this point, that is delta Vp should be 0. Otherwise this is not true, right? That is increase in the drain current by the same amount, delta IC. So that is not true otherwise. Okay. Now we had seen that one can find out the gain of this amplifier by considering a half circuit either. Okay. And we had found in the bipolar junction transistor based differential stage that the gain was minus GM RC. Okay. So here the gain is minus GM times RD. Okay. Now we understand that the overall gain of this differential pair is minus GM times RD, and the half circuit, that is the gain of the half circuit, which is actually a common source amplifier. Okay, so right, common source stage, and the gain is minus GMRD. Okay, in this case also, and this is for the complete differential pair. Okay. So we see that the gain of this differential amplifier is equal to the gain of one half of this circuit. Okay, so that means this differential pair has to work hard so that it matches the gain of a common source stage. Okay, so how hard it has to work? Okay, so that can be understood by looking at the drain currents drawn by this differential pair. That is, two drain currents are drawn. Okay, that is, M1 also draws a drain current ID and M2 also draws a drain current ID. However, in common source stage, only one drain current is drawn. So obviously that would mean that this differential pair would dissipate twice the power in comparison to a common source stage or this half circuit. Okay. So this MOS differential pair, this will dissipate twice the amount of current or power. Okay. So there is basically a trade-off between power and gain here. Okay. So this gain is achieved at the cost of power consumption, which is double in case of differential pair in comparison to this common source stage or half circuit. So I'll write common source stage or half circuit. Now one can also find out the large signal response of this MOS differential pair, okay, DC response. Okay. So for that, again, one would assume that these two transistors are acting in saturation, right? So first thing is that one has to assume that these two transistors are working in saturation. Then one has to write the drain current in saturation. Okay. So which will give you ID1 and ID2. Okay. And then also knowing that the current through these two transistors, these are same, that is, if this is ID1 and this is ID2, then one has to also assume that ID1 plus ID2 is equal to the total tail current, which is ISS. Okay. And then one can also consider that this Vp, this is common to both these two transistors M1 and M2. Okay. So one can write VGS, which would be equal to V in 1, okay, minus Vp, and this is also equal to the VGS of MOSFET number 2, which is V in 2 minus Vp. Okay. So I have another relation 1, 2, 3. Okay. And then we also have so with using these three relations, one can find out ID1 and ID2. In fact, one can find out the differential current ID1 minus ID2 using these three relations. Okay. So ID1 minus ID2 can be found to be equal to this much. Okay, considering these three relations, and also considering that the device is in saturation. So one has to write the current equation in saturation also, that we had already written earlier. So one has to use this equation also to find out the differential current, that is ID1 minus ID2. Okay. Now one can also find out the maximum differential input voltage. Okay. So this is the amount of input voltage, that is differential input voltage Vn minus Vin2, maximum differential input voltage, which drives the entire current through one of the transistors. So other transistor has nearly zero current. Okay, so the entire current, that is this ISS, flows through only one transistor. So for example, let us consider this case where two transistors are present, M1, M2, and let us say that this entire tail current is flowing through M2 ISS. Okay, and through M1 very small current or nearly zero current is flowing. Okay, so because we are also assuming that the gate to source voltage of this M1 is VTH. Okay, so that is, it is almost on, so because of which very small current is flowing through the drain of, between drain and source of this transistor. Okay. Now to find out this maximum differential input voltage, one can consider few things, that is VGS1. So one can find out that VGS1 is VTH, okay, number one. Then VGS2, okay, assuming that this M2 is in saturation, M2 is in saturation, so one can write again the equation for this current in saturation, that is ID, that is 1 by 2 mu n Cox W by L VGS minus VT whole square. Okay. So from here, because ID is known, ID is ISS, entire current is flowing through M2, so I can find out VGS2 here. Okay, VGS1 is known to me, so I can find out VGS2 of this transistor from here. Okay, so which will be simply equal to, if I try to find out VGS2, so VGS2 would be root of ID by this term. Okay, in fact 2 will also go here, so 2 ID by mu n Cox W by L, this will come down. Okay, and square root of this, okay, VGS minus VT whole square, and then VT I'll bring here, so this will be plus VT. Okay, so VGS2 is 2 root of 2 ID by mu n Cox W by L plus VT. Okay, so which is also mentioned over here. Okay, so VGS1 is known, VGS2 is known, okay, and this VGS1 and VGS2, so those are actually V in 1 and V in 2. Okay, so VGS1 and VGS2 are equal to V in 1 and V in 2. Okay, so I can find out V in 1 minus V in 2, the maximum value. Okay, so which is equal to, if I subtract VGS1 and VGS2, V in 1, right, so this gives V in 1 minus V in 2, so VTH is common here, it goes off, so I'm left with only this term. Okay, so that means the maximum differential input voltage is equal to this much. Now again, this can be written in terms of VGS minus VT, because in the drain current in saturation equation I have VGS minus VT term, so I can write this again in terms of VGS minus VT. Okay, so which is that the maximum differential input voltage is equal to root 2 VGS minus VT, okay, or VGS minus VT equilibrium. Okay, so this is the maximum differential input voltage which will cause the entire drain current to steer in one of the transistors. Okay, so that point happens in the IV characteristics here. or here. Okay. So at this point the entire drain current flows through M1, it reaches ISS. Similarly at this point the entire drain current flows through M2, okay, because ID2 reaches ISS here. Now if I try to compare MOS and bipolar based differential pairs, so I will find that the maximum differential input voltage for a MOS based differential amplifier, it is a finite value, okay. But for a BJT based differential pair, this maximum differential input voltage is uh, undefined or infinite, one can say, right? So that can also be found by going back, and yeah, so going back we had, I think, calculated something here, some relation. So I'll just go back and check whether we have calculated, yeah, here, right. So this is BJT based, okay. So I can find out this V in 1 minus V in 2 from here, okay. So assuming that the entire this current flows through one of these two transistors, so I can find out V in 1 minus V in 2 ratio from here, okay. So from here if I find out this V in minus V in 2 ratio, so this would come to be equal to, I mean, it would be undefined or infinite, okay. So that is how one can compare the maximum differential input voltages of a MOS based differential pair and a bipolar differential pair, right. So there exists a finite differential input voltage to completely switch the current from one transistor to other in MOS based differential pair, but for bipolar this voltage is infinite. Now what happens if the tail current is doubled? Okay. So if tail current is doubled, that is, instead of ISS now I have two ISS, so that would mean each transistor will draw ISS, right. So each transistor will draw ISS, okay. So for drawing this current, which is nearly double of what it was drawing earlier, my VGS minus VT, that is overdrive voltage, so that should also increase, okay. So the effect of doubling current would be that the overdrive voltage of each transistor will increase by root 2, okay. And to accommodate this change, differential input voltage maximum value, okay, so that also increases by root 2, and in this case we have also assumed that W by L remains unchanged, okay. So two things are happening, that is the maximum overdrive voltage, that is VGS minus VT maximum, so that is increasing by root 2, okay. And to accommodate this change, my maximum differential input voltage, that is V in minus V in 2 maximum, so that is also increasing by root 2 here, right. Now let us say that the tail current remains same, and now the W by L of the transistors are doubled, right. So tail current remains unchanged, okay, and W by L, so that becomes 2 times W by L, yeah, so that doubles actually, okay. So doubling W by L would also mean, since drain current is directly proportional to W by L, so the drain current will also increase. Now when W by L is increasing, so this would also mean that the equilibrium overdrive voltage, so that will be lowered by root 2, okay, because the tail current remains unchanged, okay. So tail current still remains ISS, we are not changing it, right. So this is tail current, but since we are increasing W by L, so that means the current drawn from the supply, that is ID1 and ID2, okay, so that is doubling, okay, because current is directly proportional to W by L. So this ID1 would become 2 ISS. Yeah, ID2 will also become 2 ISS, but the tail current is not changing. Okay, so this would mean that the current should become this much, and the tail current is not changing. Okay. So to accommodate this fact, the overdrive voltage, that is VGS minus VT, so this should be lowered by root 2, okay, because the current is proportional to the square of the voltage applied at the gate. Okay. So VGS minus V2, that is the overdrive voltage, so that will be lowered by root 2, and thus the differential input voltage maximum, so that will also be lowered by root 2. Okay, that is V in 1 minus V in 2, the maximum value, so this will also get lowered by root 2. Now one can also do the small signal analysis of MOS differential pair, similar to what we had done for BJT differential pair. So one can think of drawing a small signal circuit like this, okay, for a differential pair, and then one can find out the gain also from this, and also the impedances, okay, that is input and output impedance can also be found from this. Okay. And in fact we had already earlier found through the large signal model the differential input, the differential currents, that is ID1 minus 2 ID2 large signal model, which had resulted this value of the differential large signal currents. Okay. So one can find out the small signal parameters, small signal gain and impedance from this circuit. Or one can also think of dividing the small signal model circuit into two half circuits, and since it's a small signal, so VP, that is this point P here, so this will be assumed to be AC grounded. So this point represents P, which is grounded, or source is grounded. Okay. And delta VP, so that means would be 0, and the gain of this half stage or half circuit could be calculated as minus GM times RC. Okay. Okay. Now let us consider some example. For example, let us say this is my MOS differential pair. Okay, that is this one here, and we have to find out the gain of this circuit. So for finding out the gain of this circuit, I will divide or make half circuits. So the half circuit for this would be here, right, this one. So this half circuit consists of M1 transistor and a diode connected PMOS load. Okay. So for diode connected PMOS load, we had earlier found in previous lectures that the impedance looking into the drain of this MOSFET, so this is 1 by GM parallel to RO, right, and impedance looking into the drain of M1 is RO1, okay, considering lambda not 0. Okay. So one can find out the output impedance, which will be parallel combination of all these inputs, all these impedances, and the gain of this circuit remains same, that is it's a common source amplifier with drain resistance, that is minus GM RD. Okay. So this represents my drain resistance M3, okay, which is drain resistance is GM3 1 by GM3 parallel to RO3. Okay. So the gain of this amplifier is minus GM1 RD parallel to RO1. So this we have already found some time back. Okay. And RD is this value. So if I plug in this value of RD here in this gain equation, so I get the gain as GM3 parallel to RO3 parallel to RO1. Okay. So which is equal to this here. Right. Next, let us say we have another example here, this circuit, and we have to find out the gain. Again, we'll divide or make half circuit. So the half circuit of this differential pair would be this. Again, it's a common source amplifier. Okay, common source stage, and RD here, that is drain resistance, is this diode connected N-type MOSFET. Okay. And let us say this time lambda is 0. Okay. So lambda is 0, so that means the impedance of this M3 would be equal to 1 by GM3. Okay. And the gain of this half stage would be minus GM1 times RD, where RD, which is represented by this N-type diode connected MOSFET, so this is 1 by GM3. So the gain would be equal to minus GM1 times 1 by GM3. So in fact, for this circuit also we had earlier calculated the gain. So in our previous lectures you will find that for this diode connected MOSFET in common source, we had calculated earlier the gain as this much, considering lambda 0. Okay. Then let us say that we have this circuit, okay, another differential pair using MOSFET. Okay. So we have to find out the gain of this circuit. So again we'll try to create half circuits. So now this half circuits will contain RDD by 2 here and RSS by 2 here at this point, right? So RDD by 2 comes here and RSS by 2 here. So the gain of this circuit, again we have found some time back, this is a common source stage with emitter degeneration, not emitter, source degeneration, because it's a MOSFET. Okay. So one can find out the gain. In fact, we had calculated earlier, the gain would be minus GM RD by 1 plus GM RS, okay, for this circuit. Okay. And this is actually the half circuit. So I should write this is a half circuit from here. So gain is this much, where RD is RDD by 2 and RS is RSS by 2. Okay. So the total gain is this much, which is also mentioned over here. Okay. Now let us say we have a bipolar cascode differential pair, that is these two blocks, that is Q3 Q1 and Q4 Q2. So this represents individual cascodes, right? Okay. So using two NPN cascode, so this is also cascode, using two NPN cascode, a differential amplifier has been implemented here, so which is called bipolar cascode differential pair. So for finding out the gain, again we'll divide this into half. So this is my half circuit over here. Okay. Now this, for this circuit we had earlier also calculated the gain by first of all finding out the output impedance. So the output impedance of a cascode, a NPN cascode, we had found earlier in our previous lectures. Okay. So that is output impedance is this much. Okay. And the gain also we had found for this cascode as minus GM1 times R out. Okay. So R out is over here, so I'll simply bring R out over here. So the overall gain becomes minus GM1 times R out, and R out we have obtained from here. Okay. Then this is a bipolar telescopic cascode where you have an NPN cascode, two NPN cascodes and two PNP cascodes, right? So PNP cascodes as a load to NPN cascode. Okay. So for this, again finding out the gain, we'll divide this circuit into half circuit. So this is my half circuit over here. Okay. Now for this half circuit, I can find out the gain, right? So that would be actually the gain of this NPN cascode, which we have found earlier, which is minus GM1 times R out. Okay. So R out, that is looking into this point, R out. So which is equal to R if I look up and R if I look down here, right? So let us say this is R of, there is R out of P cascode, and this is R out of N cascode. Okay. Okay. So total R out can be written as R out of P cascode in parallel with R out of N cascode. Okay. So for P cascode and N cascode, both individually we have found earlier. So in our previous lectures we had found the impedance. Okay. So these impedances are that for this R out P, the impedance is this much. So this is R out P, and similarly the output impedance in case of an NPN cascode is this R out N. Okay. And gain is minus GM times R out. Okay. So the gain is minus GM1 times R out, okay, of this cascode, for which load is a PMOS cascode, right? So the gain is minus GM1 R out itself, okay. And R out is total R out is this parallel to this, that is this much, okay, multiplied by then GM1. So this gives me gain of this circuit. Okay. So gain of this half circuit is also equal to the gain of this complete differential pair, which is this much. Now we can also think of considering a parasitic resistance in between these two nodes. Okay. That is between Q7 and Q5 PMOS cascode. You have a parasitic resistance, let us say. So what is the effect of this parasitic resistance on gain and output impedance? So that can be calculated by again drawing the half circuit. Okay. And this half circuit will contain this resistance half value, right? So R1 by 2. Okay. Now for finding out the total output impedance, we know the output impedance of this remains unchanged, but R out of PMOS will be PNP cascode will be modified. Okay. That is in between Q5 and Q7 one has to consider R1 by 2 also. Okay. So that means the resistances associated with Q7 and Q5. So wherever I see the resistances, I'll have to include R1 by 2 in parallel. Okay. So that is here. So this is the R out P or ROP, that is the output impedance of PMOS cascode. Okay. Where I see RO7 and RPi5, so I'll have to also include R1 by 2 in parallel. Okay. Similarly between Q5 and Q7, I'll have to again include R1 by 2 in parallel. Okay. That is the output impedance of PNP cascode is modified. Now it is this much. Okay. And the output impedance of NPN cascode remains same, okay, which is this much. Okay. Now the gain will be again minus GM1 times R out N parallel to the modified R out P. Okay. Okay. So gain is minus GM1 times the output impedance of the NPN cascode and the output impedance of PNP cascode. Okay. So both in parallel. So that way one can find out the gain of this circuit. Next one can also try to find out the gain of a MOSFET cascode differential pair. So far we have seen BJT based cascode differential pairs. Let us try to find out the gain of a MOSFET cascode differential pair. So the calculation for this also remains similar. Okay. That is, one has to draw the half circuit first. Okay. And the half circuit here represents NMOS cascode. Okay. So for this NMOS cascode, gain is already calculated by us in our previous lectures. Considering lambda not equal to 0, the gain of this cascode is minus GM1 RO3 GM3 RO1. Okay. Similarly, similar to BJT based telescopic cascode, one can think of a MOSFET based telescopic cascode where you have a NMOS based cascode and also a PMOS based cascode. Okay. So both are cascodes of different types, NMOS and cascode. Okay. So we will have to find out, that means again the half circuit, okay. And from the half circuit I can find out the impedances looking into, the output impedance of this PMOS cascode and output impedance of this NMOS cascode, which has already been found by us in our previous lectures, which is this much, and the total gain is minus GM1 multiplied by the parallel combination of these two output impedances. Okay. Similar to the BJT base cascode. Okay. Now let us stop here itself, and we will carry on from here in the next lecture.